Hello and welcome back to Historical Geology. I am Robert Lopez, your instructor here at West Valley College. And this week I want to cover chapters 10 and 11, only because these two chapters cover the Paleozoic Earth history. So chapter 10 is the early part of the Paleozoic, and chapter 11 would be the later part of the Paleozoic. Looking at this earlier Paleozoic history, we're going to look at the Cambrian, Ordovician, Silurian in this first part here for chapter 10. Some of the highlights that we'll look at during this time, we're going to see the development of mobile belts. So these mobile belts are highlands where there are compressional activities really just along the margins of the continents as new terrains, new land masses are being accreted or attached to North America. And we call those orogenies. Remember, oro means mountain, and so a mountain genesis here, mountain building events. We also find that in the early Cambrian, we see a lot of shallow water deposition. Remember, the platform are going to be the younger sediments, mostly the Phanerozoic sediments, those that are going to this Phanerozoic eon, that overlie the Craton sediments, which are the Precambrian rocks over here. And so we'll see mainly marine deposition, even on the continent, which means we're going to have these shallow continental seas, which we call epicontinental seas, or your book here calls them epiric seas. So we'll get to those in a moment. And really, because we have this shallow continent with few mountain ranges to begin with in the Cambrian, we're going to see sea level fluctuations, transgressions where sea level rises. And when we see a transgression, we see a deposition of rock units, sandstones, limestones, evaporites. So we see the physical evidence. And then the regression is when sea level drops, and it's usually that's marked by an unconformity, an erosion event, where we don't have the rocks, but we see that erosion event. And so there's a time gap there, an unconformity. So for the transgressions, we're going to break them out into these cratonic sequences. And there are 4 of these cratonic sequences in the Paleozoic that we'll talk about. And then what could be causing these changes in sea levels? Well, maybe we're seeing advances and retreats of glaciers. What we know is happening in the Paleozoic is Gondwana is forming in the Neoproterozoic to early parts of the Paleozoic, and it's moving over the South Pole. So glaciation is a key factor for sea level fluctuations. Also because we're rifting Rodinia and we're moving continental plates around by seafloor spreading, the faster the seafloor spreading, the higher the topography of the seafloor. So if the seafloor topography is high, then it's going to push the seawater away onto the shores of continents, right? So it's going to increase sea levels. If the rate of seafloor spreading decreases, that means the seafloor will sink back down, which makes the volume of the ocean basin larger, so the seas will retreat back into the ocean basin. So that's another way we can get these fluctuations in sea level. Let's look at the document camera here. So again, this Paleozoic Earth history, chapters 10 and 11. And some of the highlights, one thing that we'll see in this chapter 10 is that there are 6 major continents. And really those continents developed because we had rifted Rodinia. So in the Neoproterozoic time, between around 750 to about 565 million years ago, the supercontinent of Rodinia that formed during the Grenville orogenies, remember the Grenville orogenies, formed that supercontinent around 1 billion years ago, and then it rifted between 750 and 565 million years ago. And so that led to these passive trailing continental margins on most continents, right? And so the 6 major continents that were rifted out of Rodinia include Baltica, which is primarily Europe and Russia west of the Ural Mountains, China, Gondwana, which is mostly the southern hemisphere continents. Remember, Gondwana is forming during this time around 750, 650 to about 500 million years ago. Those Pan-African orogenies that we talked about. And then a little microcontinent of Kazakhstania. Laurentia, important because Laurentia is North America, Greenland, parts of Scotland, and Scandinavia. And Siberia is another continent that was around those times. Going back to this rifting of Rodinia, so during this time, remember we're seeing this Precambrian basement, which is about 1.7 billion years old. We have those metamorphic rocks. If you think about the Grand Canyon, we have that Vishnu schist. Over in Death Valley, we see the Badwater gneisses and the metamorphic core complexes, and they're all intruded by these 1.4 to 1.2 billion year old plutonic rocks. Remember, in the Grand Canyon, it's the Zoroaster granite, and we have some intrusive in the Death Valley regions that also date between 1.2 and 1.4 billion years. And then we have this kind of Creighton-wide unconformity. In fact, we call it the Great Nonconformity. And in the Grand Canyon, remember, we have that Unkar group, which documents the first sediments on this great unconformity here in Arizona. And then above that, we start seeing the Cambrian. So this symbol here, a C with a line through it, means Cambrian. So for the Cambrian, we start seeing that Tonto group, which includes the Topites, the Topete sandstone, the Bridal Shale, the Mauve limestone. So we talked a little bit about these already. But while these are forming in the Grand Canyon of Arizona, over here in Death Valley, we're seeing Cambrian rocks. In fact, this Wood Canyon formation is a limestone that really spans the pre-Cambrian boundary here, right? Then we see the Zabriskie quartzite, the Carrera Formation, which are a series of limestones and some fine sands, and then the Bonanza King Formation, which is another series of limestones. So mostly we're seeing limestones, minor siliciclastic rocks over here in the west, over in the Death Valley region, but at the same time we're seeing sandstones, a shallow shoreline over in Arizona, and then it gets deeper because we start seeing the Bridal Shale, right? So top pieces of sand, shale, and then we get deeper with Jamoff. So that's recording one of these transgression events, right? Sea levels getting deeper. And you'll see that that's one of these first Creighton-wide sequences, or cratonic sequences, and that first one's going to be called the Sauk sequence, as you'll see in a moment. Another highlight of this early Paleozoic time, or really throughout the Paleozoic, is we do see these Creighton-wide sequences where we see sea level transgress over the continent, which means we're going to start seeing deposition of sandstone, then on top of that shale, then on top of that limestone, which is telling us that the sea level is getting deeper at that particular location, which means sea levels are advancing across continents. And that's where we're getting these shallow epicontinental or epyric seas. And then there's going to be a regression where that sea level drops, right? Maybe a glaciation event initiates, or sea level or seafloor spreading rates decrease. But anyways, sea level drops, and we see that an erosion event that marks a regression. And in this Paleozoic time, we're going to see 4 of these cratonic sequences. The first one, which is over that first nonconformity, right, which includes the Topites, Bright Angel, Mauve, or these formations here in the Grand Canyon region, well, that's called the Sauk sequence. And that Sauk sequence is Neoproterozoic from around maybe 600 million years to early Ordovician, right? So Neoproterozoic to early Ordovician. And then there's an unconformity because there's a regression. And then the next sequence, another advance of sea level, called the Tippecanoe sequence, which is mid-Ordovician to early Devonian. And so there we see a different type of sedimentary rocks being deposited. And then the sea level regresses, and we see another erosion unconformity event. Then sea level advances again in the Kaskaskian time, or the Kaskaskian Sea, and that's going to be middle Devonian to late Mississippian. But then there's another retreat of sea level and another erosion unconformity event here. And then finally, the last Paleozoic advance of sea level is the Absaroka Sea, or the Absaroka sequence. And that one is early Pennsylvanian, and it actually goes into the early Jurassic, which is part of the Mesozoic period. So let's over here look at slide 9, and this kind of relate a little bit to what we're seeing here with this Sauk sequence. So looking here at this slide 8 on the PowerPoint, I want you to note here, this is Laurentia, and during this time, around 514 million years ago, which is Cambrian time, we have North America, Laurentia, which is east-west, and note that the equator is pretty much going through the Great Lakes. Texas over here, Death Valley region is pretty much at the equator. The east coast of the U.S. is pretty much south of the equator during this time. And then you'll see that over or during the Paleozoic period, or eon, Laurentia is going to do a counterclockwise rotation so that it's going to be north-south the way it is today. Highlights to note here is that when we rifted Rodinia, Baltica spread away, Siberia spread away, Antarctica spread away, we opened up an ocean between Laurentia, Siberia, and Baltica. Remember, Baltica is going to be Europe primarily. And that ocean that opened up here is called the Iapetus Ocean. So this is like the Paleo-Atlantic Ocean. this Iapetus Ocean, because eventually we're going to close this ocean and then reopen it to form the Atlantic. So anyways, we have this stable platform, and in this region we're going to form that sock sequence. This sea will advance across the continent, the shallow epicontinental sea, depositing those units that are characteristic of the sock sequence. Now when we look at these cratonic sequences, note that we want to look at what's going on here. So this symbol again means Cambrian, Ordovician, Silurian, Devonian. And so that sock sequence again is going to be from the Neoproterozoic to about the mid-Ordovician. And then there's going to be this craton-wide unconformity or erosion event, which is a regression, and that's our Tippecanoe sequence will come after that. And then there's another regression here, and then well, that's the advance of Kaskaskia Sea. So anyways, this kind of documents those, at least the 4 that we see in the Paleozoic. And then you'll see there's 2 that are going to occur in the late Mesozoic during Cretaceous time, and then 1 in the Cenozoic. We'll talk about these later on. So I wanted to get some jargon out of the way, some words that we use. So one of the words, and we've talked a little bit about these already. Remember, the craton involves this whole area of Precambrian rock. So it's anywhere where Precambrian rock is either exposed or in the subsurface, right? So this whole area would be the craton in here because there's Precambrian rock beneath it. Remember, the shield is where you see Precambrian rock exposed at the surface. You can walk on that Precambrian shield, right? That would be the basement rock or Precambrian rock that's exposed at the surface. And then the platform would be the regions where the Precambrian rocks are buried by that Phanerozoic sediment. So this would be the Phanerozoic or younger sediment covering the Precambrian rocks, right? So that's kind of our model for craton shields and platforms. Then other terms that we're using are this term called mobile belts. And some mobile belts are occurring along the peripheries of continents, in this case of Laurentia. And they're elongate areas of orogenic activity. So remember, orogenic means mountain building activity. So you're either causing subduction zones or crashing island arcs up against continental margins, or crashing continents into each other, right, to make the continent collision zones. But they buckle that platform and they bend that strata. So a good example of that are the folded rocks in the Valley and Ridge province of the Appalachians, right? The Blue Ridge Mountains over there in the Appalachians are a good example of that buckled platform sediment. So all these once horizontal rocks over here are now all folded because of that collision. Some of the mobile belts that are important to North America, to Laurentia, are the Cordilleran mobile belt. So the Cordilleran mobile belt really includes everything from the west coast of Alaska really down into central Mexico, southern Mexico. So that whole Cordilleran just means mountain ranges. It includes the Rocky Mountains, the Sierra Nevada, the Coast Ranges. And you'll see that there are different orogenic episodes that led to the formation of those mountains. The Ouachita, these include like the Ozark Mountains or the Marathon Mountains of Texas down in the south of the U.S. And then the Appalachian Range, well, that's on the East Coast, so the mobile belt there. And then the Franklin would be up in the north coast, sort of the northeast coast of Alaska. So again, those are the peripheral margins of Laurentia, and that's where we're seeing the accretion of new land masses along these mobile belts. I use the word epyric. So remember, these are these epicontinental shallow seeds. So when we see these cratonic transgressions, right, where sea level rises and you start seeing sandstone, shale, limestone, that progression is telling us that there's deeper and deeper water, right? So those are called the epyric seas. So let's look at this slide 10. So this kind of shows a graphic of this Precambrian shield. So that's a craton where you can walk on. And then the platform here, this is where the craton is buried by younger sediment. And then when we're looking at the mobile belts, so the Cordilleran mobile belt, so basically the west coast of Alaska all the way down into Mexico. The Franklin mobile belt, kind of this north coast of the Laurentian shield up here, up north of Alaska and Canada. And then the Appalachian mobile belt is basically the east coast, where we're seeing the Appalachian ranges and different orogenic events that occurred there during the Paleozoic. And then the Ouachita belt would be down here in the south.